Hello and welcome to this presentation. My name is Lukas Leuenberger and I'm working at the Eastern Switzerland University of Applied Sciences. I'm presenting today our paper which describes how a fast FPGA-based ADC can be built without using any external components. I will first give a short introduction into the functionality of the used type of ADCs and how such an ADC can be built inside an FPGA. Then I will talk about the architecture of the built ADC. This includes the structure of the ADC and how the slope can be generated inside an FPGA. Further, I will talk about the used time-to-digital converter and what kind of calibrations are necessary for the ADC to provide accurate results. Finally, I will present the achieved results of the ADC. The ADC we built is based on the principle of a slope ADC. In the top picture you can see the general structure of that kind of ADC. A slope generator creates a slope out of a clock. This is shown in orange. This slope is compared to an analog input signal. A comparator, shown in green, compares the slope to the input signal and changes its output state as soon as the slope reaches the voltage level of the input voltage analog in. A time measurement block then measures the time from the beginning of the slope until the output of the comparator changes. As there is always a rising and a falling slope, the comparator switches twice its output signal, which results in two time measurements. If it is known what the slope looks like, it is then possible to translate the measured times into digital representation of the analog input voltage. But how can such an ADC be built in an FPGA? As comparator, an LVDS comparator can be used. These types of comparators are often found in the IOs of modern FPGAs. The time measurement can be done with a time-to-digital converter. This might be done using a tap delay line TDC, which can also be easily built in an FPGA. Also, it is no problem to build the control logic in an FPGA. But what about the slope generator? First, implementations used external resistors together with an external capacitor to generate the slope outside of the FPGA. This was later reduced to only one external resistor. The slope was then generated by using the parasitic capacitance of a pad. All prior implementations of FPGA-based ADCs needed external components. Our question was, are external components really required, and what can be achieved if additional correction and linearization techniques are applied? To answer this question, we will first have a look at the architecture of our ADC. A mixed-mode clock manager creates a 600 MHz clock. This clock is routed to an output delay and afterwards to an output buffer. This output buffer is connected to one input of an LVDS comparator. Note that this connection is made inside the FPGA. The analog input signal which shall be measured is connected to the other input from the comparator. The comparator switches its output state twice during a sampling period, once as soon as the rising slope goes above the input voltage, and once as soon as the falling slope goes below the input voltage. The output from the comparator is then routed through an input delay and is brought to the TDC. A tap delay line TDC is deployed in this architecture. The state of the delay chain is captured with the sampling clock and then routed to an edge detector. This edge detector determines the two positions where the comparator switched its output signal. The two detected positions are forwarded to a bin-by-bin correction block and then to a second block that corrects the voltage characteristic of the slope and the comparator. As it can be seen, two different sampling rates are possible with this implementation. A sampling rate of 1.2 GSample per second is achieved if the measurements of the rising and falling slope are treated individually, and a sampling rate of 600 MSample per second is achieved if the mean value from these two measurements is calculated. To be able to create a slope inside the FPGA, an unusual structure is required for the LVDS pair. The pin that creates the slope needs to be configured as input-output pin, while the other pin is only an input pin. However, the used tool, in our case Xilinx Vivado, does not allow that the two pins from an LVDS pair have a different I/O direction. Therefore, both pins need to be configured as input-output pins and the desired structure needs to be achieved by instantiating the required input and output buffers by hand. Two possible solutions exist. In variant A, a differential output buffer is connected to the differential input buffer. However, only one port from the output buffer is connected to a port from the input buffer, while the other port from the output buffer is left unconnected. This structure can be implemented and a valid bitstream can be generated. However, when tested on a real hardware, both outputs of the output buffer are unconnected, even though in the implemented design one output is shown as connected. Another solution is shown in variant B. Here are two single-ended output buffers instantiated and connected to the two input ports of the input buffer. One output buffer is then set to 3-state, which makes this input-output pin basically an input-only pin. This variant produces a DRC error during the placement phase. The DRC error states that a single-ended output buffer cannot drive a differential input buffer. However, this DRC error can be downgraded to a warning. If the error is re-enabled before the final DRC, which is executed before the bitstream generation, this DRC passes and a valid bitstream is generated. When tested out on hardware, this structure works as expected. With the presented structure, it is now possible to generate a slope inside the FPGA. To generate the slope, a feature which can be found in AltoScale Plus FPGAs is used. In these FPGAs, it is possible to change the output impedance of the output buffer. The slope is then generated by changing the output impedance to the highest possible value and by using the parasitic capacitance of the pad. The slowest possible slope that can be generated that way rises from 0 volt to 1.8 volt in approximately half a period of a 600 MHz clock. This also means that it makes no sense to use a slower sampling clock, as the slope cannot be made slower with that approach. Another important block in the ADC is a time-to-digital converter. This block measures the time from the beginning of the slope until the slope crosses the input voltage. We use a tap delay line TDC. On the right side you can see the general structure of such a TDC. Multiple delay elements form a chain, and after each delay element the chain is connected to the input of a flip-flop. The flip-flop then captures the current state of the chain for each sampling period. The captured state is then further processed by an encoder or in our architecture by the edge detector. In the used FPGA, we use the carry chain to form our delay chain. The carry chain consists of multiple carry elements. The structure of such a carry element is shown in the dashed box in the lower right image. Each slice in the FPGA contains 8 carry elements, whereas each has a delay of around 2 to 3 picoseconds. The MUX block inside the carry element act as delay elements. The delay between two slices is around 11 picoseconds. To increase the number of sampling points from the delay chain, the dual sampling approach can be used. Instead of using only the CO outputs after the delay elements, it is also possible to use additional O outputs. This effectively doubles the number of sampling points. However, the output O needs to be inverted as the select signal S is a logical one. Clock jitter and clock skew may lead to the problem that bubbles occur in the captured state of the delay chain. The top image shows how such bubbles look like. Bubbles are discontinuities in the captured signal and occur around the edges of the signal. For example, a flip-flop might capture the state of the delay chain too early, resulting in a measured 0 instead of a 1, because the edge has not yet traveled past that flip-flop. This means that a bubble-proof edge detector is required. Our implemented edge detector filters bubbles in a small local neighborhood. Another interesting behavior can be seen if the static timing analysis of a carry 8 element is inspected. Each slice in the FPGA contains one carry 8 element, which again contains 8 carry elements. From the structure of the carry chain, one would expect that the delays from the input of the carry 8 block to the output would rise from output CO0 to CO7. However, the last output CO7 is in reality faster than the first output CO0. Based on that information, we implemented a reordering of the outputs of the carry chain. This then helped us to reduce the average number of bubbles measured. Yet there is still another problem. the delay chain is not uniform. If a clock that is not correlated to the sampling clock is fed into the delay chain, a histogram has shown results. If the delay chain would be ideal, the histogram would be flat. However, as it can be seen, this is not the case. One reason for that is that all carry elements have a slightly different delay, and also the larger delay between two slices has an impact here. Another influence might be the fact that the rising and falling edge propagate with a different speed through the delay chain. According to some papers, one edge is up to 5% slower than the other. To overcome this problem, a bin-by-bin correction of the TDC is implemented. At startup of the FPGA, this correction block creates the histogram of the delay chain and calculates then the DNL and the INL. The measured TDC values can then be corrected using the calculated INL values. The whole correction is done inside the FPGA. To further increase the linearity and resolution of the TDC, the delay chain and some of its optimization schemes are instantiated multiple times. These parallel instances all have the same input signal and calculate then the position of the detected rising and falling slope in the delay chain. From all these results, the mean value is then calculated and used for further processing. In our measurements, we saw that 4 parallel instances offer a good trade-off between increase in resolution, decrease in DNL, and increase of required resources. 3 calibrations need to be performed prior to using the ADC. The first calibration is used to determine the length of the delay chain. With this information, it is then possible to calculate the mean delay for one delay element. The second calibration aligns the created slope with the sampling clock, and the third calibration determines the voltage characteristic of the slope and the LVDS comparator. The first calibration can be done by using only FPGA-internal elements, whereas calibration 2 and 3 require an external signal to apply to the ADC. In our experiments, we saw that it might be sufficient to execute calibration 2 and 3 during a production test and then to store the data. This data might then be read in a later run and used as calibration. The first calibration is used to determine the length of the delay chain. That means it must be identified how many delay elements correspond to one sampling clock period. To determine this length, a clock with the same frequency as the sampling clock is fed into the delay chain. This clock is phase shifted multiple times, and the ones in the delay chain are counted for each phase shifted clock. This results in one of the situations as shown in the image. Situation A occurs if the delay chain is too short. For certain clock phases, a part of the high phase is lost, and therefore the number of ones is too low. If the delay chain has the correct length, a situation as in B arises. As there is always one full clock period in the chain, the number of counted ones is constant. On the other hand, if the delay chain is too long, situation C occurs. In this situation, the high phase of the clock appears twice in the delay chain, and hence the number of counted ones is too high. In our implementation, always a situation as in C results, as we made the delay chain too long by purpose. The correct length can then be determined by taking the minimum number of counted ones and multiply that value with a factor of 2. Of course, this is only valid if the clock has a duty cycle of 50%. The delay elements which come after the determined length are then simply discarded in our implementation. The second calibration aligns the generated slope with the sampling clock. This is achieved by applying a DC voltage to the analog input of the ADC. This voltage is chosen such that the times from the rising and falling edge to the middle of the sampling clock are in the same ballpark. The pulse from the comparator is then aligned such that it appears in the middle of the delay chain. This is done by changing the input and output delays from the pad where the LVDS comparator is located. It is worth mentioning that the calibration does not need to be perfect, as this calibration only makes sure that the two edges from the comparator appear in the correct order, meaning that, for example, the rising edge is always before the falling edge and that both edges appear in a detectable region. Due to the way our edge detector works, it is not possible to detect edges in the beginning and in the end of the delay chain. The final calibration is the determination of the voltage characteristic of the generated slope and the LVDS comparator. The image shows a measurement of the falling and rising slope in orange and blue. In order to achieve accurate results, These slopes need to be corrected such that after correction they represent the green ideal slope. To achieve this, a known low frequency ramp is applied to the analog input. The digitized values of the rising and falling slope are then matched against the input voltage, and two lookup tables are calculated and then used to correct the measured values. I present you now the results of our ADC. The ADC is compared to previous publications. Wu built a slope ADC that used multiple external elements. Homeul later used only one external resistor to build a slope ADC. Xiang also built a slope ADC with an external resistor, but used a different time-to-digital converter. As it can be seen in the top image, the presented ADC achieves a higher ENOB at a higher sampling rate than the previous published ADCs. With the 600 megasample ADC, an ENOB of 7 is achieved, while the 1.2 gigasample version of the ADC accomplished an ENOB of 5.3. The voltage range is from 0.15 volt to 1.45 volt. Unfortunately, not the whole voltage range of the FPGA can be used, as the LVDS comparator has two deadbands where it does not work. It is also once again worth mentioning that this ADC does not require any external elements and hence requires also less pins. As there are no external elements required, it is for example also possible to use first the LVDS interface as such, and then later the FPGA can be reconfigured to act as ADC on the same pins without the need for a hardware change. On this slide you can see the DNL and INL for both ADC variants. The DNL is in the range of -0.9 to 0.9 bit for the 600 megasample ADC and -1 to 1.6 bit for the 1.2 gigasample version. The INL is -1.1 to 0.9 bit for the slower implementation and -1.1 to 1.2 bit for the faster variant. On the right side, the measurement of a 30 MHz sine is provided. The blue curve shows the measurement with the 600 megasample ADC, while the orange curve shows the measurement with a sampling rate of 1.2 gigasample. As you can see, the 30 MHz sine is clearly visible. Finally, some words about the used resources in the FPGA. Around 9% of the available lookup tables and 7% of the flip-flops are occupied by the ADC. The largest block is the edge detector, which is instantiated 4 times due to the parallel instances of the TDC. This block is relatively large as it is heavily pipelined in order to achieve a clock speed of 600 MHz. It is possible to not use any parallel instances of the TDC, however this is paid with the price of a little less precision. Interesting is also the latency through the ADC, meaning how long it takes until a measurement can be seen at the output of the ADC. In this ADC, the processing takes 26 clock cycles, which is equal to 43 nanoseconds. This means 43 nanoseconds after the measurement has been taken, the sample is at the output of the ADC and can then be used for further processing. This is now the end of this presentation. Thank you very much for your attention.